Somewhere in a lab in Santa Barbara, a machine cooled down to a temperature colder than deep space just did something that physicists have been chasing for almost 30 years. It did not just compute faster, it did not just break a record, it broke a curse. For 3 decades, every serious quantum computer on Earth has lived under the same death sentence. The bigger you build it, the worse it gets. More qubits should mean more power. Instead, more qubits meant more chaos, more noise, more errors, until the entire promise of quantum computing looked like it might collapse under its own complexity. And then Google's quantum team flipped that rule upside down. They built a chip, ran an experiment, and watched the error rate go down instead of up as they made the system bigger. If you are not a physicist, that sentence might sound small. It is not small. It is one of the most important technical results in modern computing history, and almost nobody outside the field fully understands what just happened or why it matters. This is not a small update. This is not a marketing slide at a tech conference. This is the moment that quantum computing stopped being a beautiful theory trapped in physics journals and started becoming something that could, within years, reshape medicine, encryption, artificial intelligence, energy, and the global balance of power. And the strange part is, most people have no idea it just happened. Let's talk about why this actually matters, because the stakes here are enormous. Right now, every computer you have ever used, your phone, your laptop, the servers running ChatGPT or Google Search, all of them work the same basic way. They store information as bits, and a bit is either a 0 or a 1, nothing in between. Every photo, every video, every banking transaction, every encrypted message you have ever sent has been built from long strings of these simple zeros and ones. It is the foundation of the entire digital world. Quantum computers throw that foundation out the window. Instead of bits, they use qubits, and a qubit can be a 0, a 1, or astonishingly, some mixture of both at the same time. Scientists call this superposition. Imagine flipping a coin, and instead of landing on heads or tails, it spins in the air representing both possibilities simultaneously until the moment you look at it. That is roughly what a qubit is doing. Now take that strange property and multiply it across dozens, hundreds, or eventually millions of qubits, and you get something called entanglement, where qubits become linked together in ways that let the system explore an almost unimaginable number of possibilities all at once. A classical computer checks possibilities one at a time, very fast, but still one at a time. A large enough quantum computer can, in theory, explore vast numbers of possibilities simultaneously. That is the entire reason governments, universities, and the biggest technology companies on the planet have poured billions of dollars into quantum research. If you can build a machine like that and make it actually work, you do not just get a faster computer, you get a fundamentally different kind of computer, one that could simulate new medicines at the molecular level, design materials that do not exist yet, optimize global supply chains in ways classical systems cannot, and yes, potentially break the encryption that protects almost every secret on the internet today. But here is where the story gets stranger, because qubits are incredibly fragile. The same delicate quantum properties that make them powerful also make them almost impossibly easy to disturb. A stray vibration, a tiny fluctuation in temperature, even cosmic rays passing through the chip can knock a qubit out of its quantum state and corrupt the calculation. Classical computers deal with errors by making copies of data, so if one copy gets corrupted, you check it against the others and fix it. But the laws of quantum mechanics literally forbid you from copying a qubit's exact state. It is called the no-cloning theorem, and it has haunted quantum engineers since the field began. So researchers had to invent an entirely different kind of error correction, one that spreads information across many physical qubits without ever directly copying it, group them together into something called a logical qubit, and use real-time monitoring to catch and correct mistakes before they ruin the calculation. For nearly 30 years, this was the holy grail nobody could fully prove. You could build small error correction experiments, but every time researchers tried to scale them up by adding more qubits, the extra qubits introduced more opportunities for things to go wrong. The system would get more complex, but it would not get more reliable. It was an uphill battle that seemed, to some experts, almost unwinnable. The whole field had a name for the line that separated success from failure. They called it the threshold, the critical error rate below which scaling up actually starts to help you instead of hurting you. Cross below that threshold and bigger means better. Stay above it, and bigger just means worse. Reaching that threshold in a real, fully verified system, without cutting corners, was considered one of the defining open problems in all of quantum computing. Google says they finally got there. And this is why the biggest companies in the world are paying close attention. The chip behind this result is called Willow, and the story of how it was built is itself a story of obsession. Google's quantum effort traces back over a decade to when the company founded its dedicated quantum AI division with one explicit long-term goal: build a useful large-scale quantum computer that could actually solve real-world problems, not just academic puzzles. Along the way, their previous chip, known as Sycamore, made headlines years ago by performing a calculation that would have taken classical supercomputers an enormous amount of time, sparking a fierce, sometimes bitter debate in the scientific community about whether that result really proved what was being claimed. Willow is the successor to that chip, and it was specifically engineered to answer the criticisms that had piled up around Sycamore. Willow packs a little over 100 physical qubits onto a superconducting chip, fabricated in-house at Google's own facility, because at this level of precision, you cannot simply outsource your hardware to someone else and trust it will work. The chip has to be cooled down to temperatures colder than outer space, inside massive refrigeration units called dilution refrigerators, because even the faintest trace of heat is enough to destroy the delicate quantum states researchers are trying to preserve. Inside that frozen, almost perfectly isolated environment, Google's team ran an experiment that became the centerpiece of a major paper published in the journal Nature. They took the physical qubits on Willow and grouped them into larger and larger logical qubits. First, a small 3x3 grid, then a 5x5 grid, then a 7x7 grid containing over 100 physical qubits working together as a single logical unit. And here is the breakthrough moment. Every time they scaled up the grid, the error rate of the logical qubit did not increase. It was cut roughly in half, 3x3 to 5x5 to 7x7, and each time the system became more reliable, not less. That is what scientists mean by exponential error suppression, and it is precisely the behavior the field has been chasing since quantum error correction was first proposed by mathematician Peter Shor back in 1995. The technical term for what they achieved is below threshold. It means Google's system has crossed into the regime where, in principle, adding more qubits leads to an unlimited improvement in reliability instead of an unlimited pileup of chaos. It is the difference between a fire that spreads no matter how much water you throw on it, and a fire that finally starts shrinking the more water you add. For the first time, in a fully verified experiment without relying on shortcuts like throwing away bad results to artificially inflate the numbers, Google demonstrated this below-threshold behavior on a real chip. There is a second part of this story that is just as important, and it is the part most people are missing entirely. Catching errors is one thing. Catching them fast enough to actually do something useful about them in real time before they ruin your calculation is another challenge altogether. Google paired Willow with a machine learning system developed by its sister lab, Google DeepMind, specifically trained to decode and interpret quantum errors as they happen. This decoder, sometimes referred to publicly as alpha qubit, works almost like a translator standing inside the chip's frozen heart, reading the noisy, chaotic signals coming off the qubits and figuring out instantly what went wrong and how to fix it before the mistake can spread. This is one of the first compelling demonstrations of real-time error correction on a superconducting quantum system, and without it, the exponential error suppression Google measured would not have been usable for any practical computation, because errors that are caught too slowly are errors that have already destroyed your answer. And this is why the biggest companies are worried, because Willow did not stop at error correction. In the same announcement, Google revealed that Willow had completed a standard benchmark computation known as random circuit sampling in under 5 minutes. The same task, run on one of the world's fastest classical supercomputers, was estimated to take something in the range of 10 septillion years. To put that number in perspective, that is roughly a 1 followed by 25 zeros. It is a number so large it has no real meaning to a human brain. It vastly exceeds the entire age of the known universe, which is about 8 billion years old. Google later went further, reporting that a newer algorithm run on Willow, called quantum echoes, performed a molecular simulation task roughly 13,000 times faster than the best classical estimate, with results that were independently verifiable and repeatable on other quantum hardware, addressing one of the biggest criticisms that had haunted earlier quantum supremacy claims. But before we get there, you need to understand one thing. Skeptics in the field, and there are plenty of serious, credible skeptics, are quick to point out that these benchmark tasks, while scientifically meaningful, are not yet solving problems that matter to ordinary businesses or governments. Random circuit sampling is essentially a stress test, a way to prove the chip is doing genuinely quantum behavior that classical computers cannot replicate. It is not, by itself, designing a new drug or breaking a bank's encryption. Researchers at Microsoft and other competing labs have pushed back on parts of Google's error rate claims, noting that depending on how you measure it, the actual error rate could be closer to 1 mistake in 100 operations, rather than 1 in 1,000. Google's response has been that the precise number matters less than the trend, the fact that performance keeps improving as the system scales, which is the entire point of proving you're below threshold in the first place. This tension between genuinely historic scientific progress and the gap that still remains before quantum computers solve everyday problems is the honest, complicated truth sitting underneath all the headlines. The real danger and the real opportunity is not what most headlines are talking about. It is what comes next, because Google is not stopping with Willow. In a sign of just how seriously they are taking the long game, Google Quantum AI recently widened its bet by adding an entirely second hardware approach, neutral atom quantum computing, where individual atoms held in place by precisely tuned lasers act as qubits instead of the superconducting circuits used in Willow. The company frames the two technologies as complementary, one strong in circuit depth, meaning how many operations it can perform in sequence, the other potentially stronger in raw qubit count, meaning how many qubits you can pack into a single system. Running both approaches in parallel is an enormous bet, requiring its own dedicated teams, its own fabrication processes, and its own massive budget. But it tells you something important. Google does not believe a single hardware approach is guaranteed to win this race, so they are hedging across multiple paths at once, much like a country fielding multiple weapons programs, because nobody is certain which one will ultimately prove decisive. Google has also laid out a roadmap, a 6-milestone plan that culminates in their stated long-term goal: a large-scale, error-corrected quantum computer, controlling somewhere in the range of 1 million qubits, fully fault-tolerant, capable of running algorithms with real commercial and scientific value that no classical computer could ever replicate. The company has publicly targeted reaching that kind of fault-tolerant capability sometime around the end of this decade, though they are careful and honest in acknowledging that the engineering challenges between today's chip and that future machine remain enormous. Going from 100 or so qubits to 1 million qubits is not simply a matter of building more of the same thing. It requires entirely new approaches to chip fabrication, cooling, control electronics, and error decoding at a scale nobody has ever attempted. This is where the entire equation changes, because Google is not the only player in this race, and the competition is fierce, global, and increasingly tied to national security. IBM has its own ambitious quantum roadmap, pushing toward large-scale fault-tolerant systems through its own superconducting chip lineage and a strategy of modular quantum computers linked together. Microsoft has poured enormous resources into a different approach entirely: topological qubits, which the company argues could be inherently more stable and less error-prone than the superconducting approach Google has bet on, though that technology remains earlier in its development and has faced its own share of scientific controversy and walked back claims in past years. Companies working with trapped ion technology and an emerging wave of startups exploring photonic quantum computers built from light itself are all racing toward the same below-threshold milestone Google just claimed to reach, each betting that their underlying physics will ultimately prove more scalable. And then there is China, whose government and research institutions have made quantum computing an explicit strategic priority, pouring state-backed investment into quantum research as part of a broader technological competition with the United States that spans semiconductors, artificial intelligence, and now increasingly the quantum realm. Chinese researchers have published their own quantum supremacy-style results in recent years using different hardware approaches, and Beijing has made clear through its national planning documents that it views quantum technology as a domain where falling behind is not an acceptable outcome. This is no longer just a scientific rivalry between research labs, publishing papers in competing journals. It has become a geopolitical contest, with echoes of the chip war already playing out around companies like NVIDIA and the global semiconductor supply chain. Whoever builds the first truly large-scale, fault-tolerant quantum computer will not just win bragging rights. They could gain capabilities with direct implications for military cryptography, intelligence gathering, advanced materials research for defense applications, and economic competitiveness across entire industries. Which brings us to the part of this story that should genuinely concern anyone who cares about digital security, because much of the encryption protecting the modern internet, the systems that secure your bank account, your medical records, government communications, and classified military data relies on mathematical problems that are extraordinarily difficult for classical computers to solve, but that a sufficiently powerful, fault-tolerant quantum computer could, in theory, crack. This looming threat has a nickname in the security world: Q-Day, the day a quantum computer becomes powerful enough to break the encryption standards the entire digital world currently depends on. Today's quantum computers, including Willow, are nowhere near powerful enough to actually break modern encryption. That requires not just more qubits, but specifically more error-corrected, fault-tolerant logical qubits operating reliably together, something still years away by most credible estimates. But the below-threshold breakthrough Google just demonstrated is precisely the kind of foundational progress that narrows the gap between today's experimental machines and that future capability. Analysts and security researchers have noted that this milestone makes the timeline for Q-Day feel less distant and more concrete than it did even a year or two ago, which is exactly why governments and major technology companies around the world have already begun racing to adopt post-quantum cryptography, new encryption standards specifically designed to resist attacks from quantum computers before a working quantum codebreaker ever exists. If you are running a business or storing sensitive data today, security experts increasingly warn that data harvested now by adversaries could simply be stored and decrypted later, once quantum computers catch up. A strategy sometimes called harvest now, decrypt later. That risk does not require Q-Day to arrive tomorrow. It only requires someone to be patient. If this story makes you want to understand the next layer of how this technology actually plays out, hit subscribe, because this is exactly the kind of turning point we cover as it unfolds. Let's talk about who actually wins and who could lose as this technology matures, because the consequences ripple far beyond Google's own labs. Pharmaceutical companies are watching closely because simulating molecules and chemical reactions at the quantum level, something classical computers struggle with because molecules themselves obey quantum mechanics, could dramatically accelerate the discovery of new drugs and materials. Energy companies are interested because quantum simulations could help design better batteries, more efficient solar materials, and even new approaches to nuclear fusion research. Financial institutions are exploring quantum algorithms for portfolio optimization and risk analysis, tasks that involve searching through enormous combinations of possibilities, exactly the kind of problem quantum computers are theoretically suited for. Logistics and manufacturing companies are eyeing quantum optimization for supply chains so complex that classical computers can only approximate good solutions rather than find truly optimal ones. On the other side of this equation sit the institutions that stand to lose the most if they fall behind. Companies whose entire business model depends on data security, banks, healthcare providers, government contractors, face an urgent and expensive transition to quantum-resistant encryption, a process security experts warn could take years to fully implement across the sprawling legacy-laden systems many large organizations still rely on. Smaller nations and companies without the billions of dollars required to build or access cutting-edge quantum hardware risk being locked out of the next wave of computational advantage entirely, creating what some researchers have started calling the quantum divide, a gap between those who control this technology and everyone else who simply has to live with the consequences of decisions made inside a handful of elite labs in the United States, China, and a few other countries. There's also a less obvious connection here, one that ties directly back to the broader AI boom reshaping the global economy right now. The same hyperscale data centers powering today's artificial intelligence systems, the massive facilities run by Google, Microsoft, Amazon, and others, are increasingly intertwined with quantum research, both in terms of shared infrastructure investment and in terms of the AI techniques, like the machine learning decoder behind Willow's error correction, that are now essential to making quantum hardware actually work. NVIDIA, the company that became the face of the AI chip boom, has been expanding into the quantum space as well, building tools and accelerated computing platforms specifically designed to support quantum research and simulate quantum systems on classical hardware. The line between classical AI infrastructure and quantum computing infrastructure is blurring in real time. The companies that already dominate one side of that boundary are positioning themselves to dominate the other side too. The real story is not the machine itself. It is what the machine makes possible, and right now, what it makes possible is still mostly potential rather than reality. It is worth being honest about that, because hype without context does a disservice to a genuinely remarkable scientific achievement. Willow has roughly 100 physical qubits. The roadmap Google has described publicly aims for a system controlling something on the order of 1 million qubits before they consider the technology truly fault-tolerant and ready for the kind of large-scale commercial and scientific applications people imagine when they hear the words quantum computer. Getting from 100 qubits to 1 million qubits is not a simple matter of scaling up manufacturing. Every layer of the system, the chip fabrication process, the cooling infrastructure, the control electronics that manage each qubit, the decoding algorithms that catch errors in real time, all of it has to be reinvented and re-engineered at a scale nobody has achieved before. Google's own researchers have been candid about this, acknowledging publicly that there's still a long way to go and that proving below threshold behavior in a relatively small system is a critical first step, not a finish line. Independent experts outside Google have echoed both the excitement and the caution in roughly equal measure. Physicists not involved in the research have called the below-threshold result a genuine, unfakeable sign that the underlying physics is working the way error correction theory predicted it should, something that is difficult to overstate given how long the field had been chasing this exact proof. At the same time, those same experts are quick to note that commercial, world-changing quantum applications, breaking encryption, designing miracle drugs, revolutionizing global logistics, are still likely years, not months, away, and depend on engineering challenges that remain unsolved. The honest picture sitting underneath all the excitement is this: the fundamental physics question, can quantum error correction actually work the way theory says it should, has now been answered convincingly, with real data published in a leading scientific journal and independently scrutinized by the broader physics community. The engineering question, can you actually build a million-qubit machine that takes advantage of that physics reliably, at scale, in a commercially useful way, remains open, and nobody, not Google, not IBM, not Microsoft, not any government, can promise exactly when that question gets answered. But here is why that distinction matters more than it might seem. Throughout the history of technology, the gap between proving something is physically possible and actually building it at scale has often closed faster than experts predicted, once the fundamental science was settled. The transistor, the technology underlying every digital device on Earth today, went from a fragile, unreliable laboratory curiosity to the foundation of the entire modern economy in a matter of decades, once researchers proved the underlying physics actually worked the way theory said it should. Quantum computing may be standing at a similar inflection point right now. The below-threshold result does not guarantee a million-qubit quantum computer arrives on schedule, but it removes one of the most serious scientific doubts that has shadowed this entire field for 30 years. The doubt that scaling up quantum systems might simply be a dead end, that more qubits would always mean more chaos, no matter how clever the error correction got. That doubt has now been directly, experimentally addressed, and the answer, at least in this one carefully controlled experiment, was no. Bigger can mean better. The exponential curve bends in your favor, not against you. So where does this leave us? We are watching the opening chapter of a technology race that will likely define computing, security, and global power for the rest of this century, the same way the race to build transistors and microchips defined the last one. Google's Willow chip, paired with its DeepMind-built error decoder, has provided what many in the field are calling the clearest, most rigorous proof, yet that large-scale, fault-tolerant quantum computing is not science fiction. It is an engineering problem now, not a physics mystery. And engineering problems, however difficult, tend to get solved once enough money, talent, and institutional will get thrown behind them, and right now, all three of those things are being thrown behind quantum computing, at a scale the world has rarely seen outside of wartime research programs or the original space race. If this technology matures the way Google's roadmap envisions, it could rewrite how we discover medicine, how we secure information, how nations compete for technological dominance, and how every major industry from finance to energy to defense plans for the future. If it stalls, if the engineering challenges between 100 qubits and a million qubits prove harder than anyone currently expects, the timeline could stretch out for decades rather than years. Nobody, including the scientists who built Willow, can tell you with certainty which of those futures we are heading toward. What they can tell you, with real, peer-reviewed, independently verified data, is that the door that seemed sealed shut for 30 years just cracked open. And once a door like that opens, in the history of science and technology, it rarely closes again. The world spent decades wondering whether quantum computers could ever truly scale. That question now has an answer, and the answer is yes, at least in principle, at least in this experiment, at least for now. The race to turn that yes into a machine that changes medicine, security, and global power has officially begun. And almost nobody outside a handful of labs in Santa Barbara, Beijing, and a few other corners of the world fully understands just how close that race has gotten. If you want to understand where this goes next, before the rest of the world catches up to what just happened, make sure you are subscribed, because this story is only getting started.